Hello everyone, welcome back to another video. In this video, we'll be discussing about a concept which is efficient heap constructor. Now, this question is an extension of the previous question that we have done, which is writing a heap, right? Writing a priority queue using heap, right? So only jump onto this question if you have already solved that problem before. And let's get started with it, right? So what does this concept say, right? Up till now, with the heap that we have created, what we did was we added a single value every time to a heap, right? So if I have a heap over here, as we know that heap is represented as a complete binary tree, right? If I'm adding a value, what would happen is it would add at the end, and then I would call for up-heapify function, right? Right? Then I would call for up-heapify function so that this value reaches its correct position, right? This is what we were doing up till now. But what if I say that I want to create a priority queue, I want to create a heap constructor such that it is able to take an entire array and fill all of those values inside that array, all of those values in one go, right? So the very basic and the naive approach that someone would do is something like this over here. So here we have a priority queue constructor which takes in array as a parameter, right? Then what it does is it calls the add function from over here, which is this. It calls the add function for each and every value in that array, right? So if we go to the main function, what I'm doing is I'm having an array and then I'm creating the object for priority queue class, and over here while calling for the constructor I'm passing that array. This would receive that array, then for every value in that array it would call for the add function, and one by one it would add those values to our heap, right? This is what we are doing. So if we think about it, what's happening is if I have a heap, right? If I have a heap, we already know that if I have a heap like this, if I have to add a value, what would happen is this value would be attached at the end, right? This value would be attached at the end, and then up-heapify function would be called, right? From this point, right? So it would travel back up until it reaches its correct position. So if we look over here, the add function adds the value in the data array list which you have over here at the very end, and then it calls for up-heapify function with the last index, right? So doing this for each and every value in the array, value in the array would result in a higher complexity of n log n, right? Let's see how. If I have this tree, right? If I have this particular tree, right? Now, this tree has a total of how many nodes? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Right? So if we count again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, a total of 15 nodes. Right? Let's suppose I say that I'm passing an array to the constructor with 15 values, right? Then this is the type of heap that would be created, right? Now how would this heap be created? Now for the very first element which would enter over here, right, the complexity would be of 0, right? Because there is nothing to up-heapify from here, right? Because it's the very first element. For these two elements, however, the complexity would be of 1. For these elements, 4 elements, the complexity would be of 2. Why is that? Because each of the node out of these 4 nodes, if I call for up-heapify from this particular level, what it would do is it would travel along the height of the tree, right? And while traveling along the height of the tree, it would check if the parent is bigger or not, and if it's bigger, what I would do is just swap, right? This is my heapify function, up-heapify function, right? So for this particular level, as there are 8 nodes over here, all of these 8 nodes would have a time complexity of about 1, 2, and 3, right? So 3 is the height. So these are just heights, right? So what I can say is for the very last level, for n nodes, right? If there are n nodes, n is equal to 15. What I can say is if there are 8 nodes over here, there are at least n by 2 nodes. N by 2 nodes are present in my last level, right? And for all of those nodes, those nodes, we are having a time complexity of h, right? This is my h, this is my h minus 1, this is my h minus 2, and this is my h minus 3, right? This is my total height of the tree, right? H is my total height of the tree. Okay, so for all the nodes in the last level, which are n by 2 nodes, I have a time complexity of h to move them up, right? Then for all the nodes that are on this level, right? How many nodes are there on this level? If we see, we have 8 nodes over here, and then we have 4 nodes over here, right? So the number of nodes would be always less than n by 2, right? Which are actually n by 4. So we have n by 4 into h. Then we would have n by 8 into h. Then h minus 1 over here, right? Because that's h minus 1. Then h minus 2 over here. And then n by 16 into h minus 3. We go on, what we would have is n by some k value, 2 to the power k value, for which my h would become 0. Right. Okay. If we just ignore even all of these, right? If we just ignore all of these, and if we just focus on this part, right? If we just only focus on the very first term, what we have is n by 2 multiplied with the height of the tree. Now, if we recall, our heap follows two properties, which are complete binary tree property and heap order property, right? So if we look at the first property of complete binary tree, every complete binary tree would always have a height of log of n, right? So I can write my h as log of n, right? This is n log n complexity, right? This is n log n complexity. So as I said, if I had to enter all the values inside my array one by one and pass it through the add function, so that my add function calls for up heapify, then the complexity is n log n. What we can do is we can make it more efficient, and we can drop this to O of n. So let's see how, right? Let's see how. This is what this video is all about, writing an efficient heap constructor, right? So again, what I'm going to do is pass my array to the constructor, and then I would tell my constructor to put all of those values one by one inside my data array list, right? So what I'm going to do is I'm going to put all of my values in my array as it is in my data array list, which is the operation of O of 1, right? Adding something to the data array list is operation of O of 1, right? Okay. Then what I'm going to do is if I have a heap over here, and if this heap is currently not following the property of heap order property, right? This would be a complete binary tree, but it won't be following a heap order property, right? So what I can do is I can tell my last subtree over here to call for down heapify, right? So from the blue line, I'm marking all the calls of down heapify, right? So I would tell this one to call for down heapify. This would create this into a proper heap, right? Every time I'm calling for a down heapify, this section would be created and this would be a perfect heap, right? Again, what I would do is I would call for down heapify from over here, then from over here, then from over here. Now all of my subtrees in my till my second last level are a complete binary tree, as well as they follow heap order property, right? Now I would call for down heapify from this point, and then from this point, and at last from my root. So now if we see, heap follows both complete binary tree as well as heap order property, right? So let's discuss about its time complexity, right? Theoretically, this should make our heap perfect. Let's discuss about its time complexity, right? So the very first level that we have over here, right? The very first level has in by 2 nodes, right? That we have already discussed. What we can also do is we can determine each and every level as a number, which is 1 and 2. Let's suppose we have, erase this. Let's suppose we have 3 over here and then 4 over here, right? So if these are my levels, then the number of nodes at each level would be 2 raised to the power my current level minus 1, right? I can write it as height, right? Current height minus 1. So if this is my height according to my nodes, right? In terms of my nodes, if this is my height, then the number of nodes over here would be 2 raised to the power h minus 1. So let's see if it's correct or not, right? For h equals to 1, 2 raised to the power h minus 1 would be nothing but 2 raised to the power 1 minus 1, which is 2 raised to the power 0, which is 1, right? And we have just a single node over here. So this seems fine. Let's verify it with rest of them, right? So what I'm going to do is, let's first create a much more clear tree, right? So let's suppose I have this, then this, then this, and then this, and then this, then this, this, and this, and this, and these. All right. Okay. So this is our complete binary tree, which is a heap, right? So if we talk about, if we think about it, we had formula of 2 raised to the power h minus 1, right? So this height is 1. So 2 raised to the power 1 minus 1 would give me 1 over here, right? So 2 raised to the power 1 minus 1. Over here it would be 2 raised to the power 2 minus 1, which is 2 raised to the power 1. 2 nodes, right? Then we have 2 raised to the power 3 minus 1, which is 2 raised to the power 2, which is 4 nodes. And at last we would have what? 2 raised to the power 4 minus 1, right? So this is my formula according to which these are my number of nodes, right? At each and every level, right? Now, what I'm saying is, what is the time complexity? We have to analyze the time complexity. Now, if we talk about the root, we are calling for down heapify from over here, right? So a root would have a time complexity. If we talk about time complexity, we would have it running for the entire height of the tree, right? Then I would have this one running for 1 minus height, right? As we see, our height is 3, and this is running for, this particular level is running for 1 and 2 times, right? So 3 minus 1, right? Which we have written over here. So again, my root is working for the entire tree, right? So the time complexity is the height of the entire tree. Then my nodes at this level, the first level, are working for h minus 1, right? So then these nodes, second last level, nodes of second last level are working for how many? These are working for h minus 2, right? So if you think about it, h is equal to 3, then 3 minus 2 is nothing but 1, right? So they are working for 1 level, right? So this seems correct, and at last, if we think about it, if there were multiple levels over here, my last nodes are working for 0 time, right? Because I said I would start doing up heapify from this level, this particular level, right? So I won't be touching the last level. Okay, so my last level would have 0, and this is because it would be h minus h over here, right? So let's write h minus h for now. So these are my time complexity, right? So what would be my total time complexity? Let's write this, right? So if I had to write, if I would have to sum all of these up, right, to find my total time complexity. So if I have to write my time complexity as t of n, it would be nothing but 2 raised to the power, the very first level, which is 1 minus 1, right? So we have 1 minus 1 working for h. Then I would add what? 2 raised to the power 2 minus 1 working for h minus 1 levels, right? So if we see, this is my second level, right? H minus 1 into 2 raised to the power 2 minus 1, right? Again, we continue with this, we would have 2 raised to the power 3 minus 1 for h minus 2. And if we go on, what I would have at the end would be something like 2 raised to the power h minus 2, which is my second last level, into 1, right? Because my second last level is working for 1. If you see over here, this is my h minus 2, right? H minus 2, and here we have 1 level, right? We have complexity of 1 level, right? Now, again, if we see the last level, which would be h minus 1, would have a time complexity of 0. So this would be my total time complexity, right? I hope it's clear. So if we write this more properly, I can say this is just 2 raised to the power 0 into h plus 2 raised to the power 1 into h minus 1 plus 2 raised to the power 2 into h minus 2 plus 2 raised to the power h minus 2 dot 1, and this would be 0 entirely. So I can discard it, right? As we are multiplying it with 0, we can discard that, right? So this is our total time complexity, right? As this is my AGP. If you look closely, this is my AGP. We are adding on some values and we are also having factors over here, right? For 2. So how do we solve this? How do we solve this time complexity? For that, let's take double of this time complexity first, right? So that would give me what? That would give me over here, if we see, we would have 2 raised to the power 1 of h, right? This is because if I multiply 2 with this, I would get 2 raised to the power 1 of h, right? Then if I multiply 2 with this, what I would get is 2 raised to the power 2 of h minus 1, right? Then if I multiply 2 with this, I would get 2 raised to the power 3 of h minus 2. And then if I keep on going, the last one would become 2 raised to the power h minus of 1, right? If you see, we have 2 raised to the power h minus 2, and if you multiply this with 2, then 2 would go up. That means h minus 2 plus 1 would happen, and then h minus 1 would become, right? Which is what I have written over here. Okay, yeah. So if we go back, so yeah, this is the time complexity that we had, right? Okay, so we have 2n now. What I'm going to do is, if this is my equation 1 and this is my equation 2, what I'm going to do is I'm going to subtract equation 1 from equation 2, right? So I'm going to do this, right? What would this mean? This would mean if my equation 2, if we look at the left hand side, we have what? 2 of Tn minus, what is my first equation? T of n, right? This is nothing but T of n, right? So if I subtract this minus this, I would get x, right? Of course. So let's see what we would get, right? If I had to subtract this from this, right? So if I had to subtract 2 raised to the power h minus 1 from 2 raised to the power h, right? This is my first term that I have to solve, these two terms, right? So let's see what I would get. 2 raised to the power 1 h minus 2 raised to the power 1, right? So we can get, what we can do is we can take 2 raised to the power 1 as common. Then what we would have, h from here minus h plus 1 from here, right? H minus h would be cancelled out. What we would get is 2 raised to the power 1, right? So let's write this, right? Let's say this gets down without being subtracted from anything, right? Then if we did this, if we subtracted this, we saw that we get 2 raised to the power 1, right? Let's do this for these two terms now. Okay, so what if I do 2 raised to the power 2 h minus 1 minus 2 raised to the power 2 h minus 2. Again, if you see 2 raised to the power 2 h minus 1 and then minus h plus 2, right? What would this be? This would cancel out. 2 minus 1, which is 1. So we get 2 raised to the power 2 into 1, which is nothing but 2 raised to the power 2. So we get 2 raised to the power 2 from here, right? So if we go on, similarly, if we go on, what we would get is 2 raised to the power 3, then 2 raised to the power 4. And if we go on till the last, we would get 2 raised to the power h minus 1, right? We would get 2 raised to the power h minus 1. Now if we look closely, if we can arrange this again, and we can write this at the end, and we can say that this is 2 raised to power 1 plus 2 raised to power 2 plus 2 raised to power 3 plus 2 raised to power 4 plus 2 raised to power h minus 1, right? And then minus 2 raised to power 0 of h. Now this is nothing but my h, right? Because 2 raised to power 0 is 1. So we can write minus of h over here, right? Minus of h over here. Okay. If we look at this closely, if we look at this particular part closely, this is nothing but my GP, right? And what we have to do to solve this is we have to use the sum of GP formula, right? So if you remember, sum of GP was nothing but a raised to the power a raised to the power ar raised to the power n minus 1 upon r minus 1, right? This is my formula, right? In which my a is the term with which I begin, r is the term that is my ratio, n is the numbers, and minus 1 is constant, right? So if we think about it, what we can do is over here we can introduce 2 raised to the power 0, right? And over here we can subtract 2 raised to the power 0, right? Won't do any harm. And using this, what we can have is my starting element is now 1, right? My ratio is of 2. The number of elements are now h, right? And I subtract 1 from it, right? If we see down here, we have 2 as ratio and we subtract 1. So this is my sum of GP. So this entire term is now equivalent to this, minus we have h minus 2 raised to the power 0 over here. If we solve this, what we have is 2 raised to the power h minus 1. This becomes 1 minus h minus 1, right? So we have 2 raised to the power h minus 2, right? If you think about it, h is our height. In complete binary tree, as we discussed, the height is equal to log of n, right? So what we can say is that this is our t of n is log of n minus log of n minus 2, right? 2 raised to the power log of n is nothing but n, right? 2 raised to the power log of n is nothing but n. So it would be n minus log n minus 2. So our time complexity at the end, what we get is this, right? And this is nothing but O of n, right? This is nothing but O of n. So if we call for down heapify, if we call for down heapify from this point, right? Again, if we call for down heapify from this point and from this point, then from this point, and then from this point, and then again from this, and then at last for the node, the root node, what we get is a time complexity of O of n, right? So this is what we have mathematically proved, right? So let's see if it works or not. So for that, we can code it directly. If we come to our console, right, what we can do is over here, instead of adding each and every value using the add function, we can add these value to the data array list that we have, right? Now what do I have to do? I have to call for down heapify. From which position? From a position just above my last node, right? Just above my last level, right? So if we see over here, as we discussed, the last level has a total of about n by 2 nodes, right? So this node would be nothing but n by 2 minus 1, right? So if we see the index that I have to down heapify, the very first is nothing but data dot size, which are my number of nodes, divided by 2, which are the number of nodes in the last level, minus 1, right? And this would go on till my I is greater than equal to 0. That means I is 0, and I will decrease the value of I. Now what I have to do is simply just call for down heapify, right? And I would call this for ith value, right? Now this should give me, if we look over here, what I have done is I have taken an array of random values. I have passed that array in my priority queue, and then I'm printing all of those values one by one after removing it from priority queue. That means I should get the most minimum value, which is 3 first, then which is 2, right? The least minimum value, right? The least value, which is 2, then I should get 3, then I should get 9, then 10, then 17, then 18, and then 22, right? This should be my output, right? So let's run this and see if it is correct or not, right? Let's see. So this runs, and if we see, we are getting the same output as over here. That means our priority queue is working just fine and our logic was also appropriate, right? So I hope you understood what we did and how we did it. And I hope you understood the whole mathematical part in which we proved how downheapifying from particular position would lead to lower complexity of O of n, right? So even if you think about it, what we are doing is, for the least number of nodes, we are having the highest complexity over here, right? Because we have just one node over here, we are having h complexity with that node. And for the last level, where we have n by 2 number of nodes, which are maximum number of nodes in level, we are having a time complexity of 0, right? But if we look at the case of upheapifying, what we were doing is, for maximum number of nodes, which were n by 2, we were having time complexity of h, and for the minimum number of nodes, which were 0, we were having time complexity of 0, right? So the only difference is that the time complexity while upheapifying, if we write over here, while upheapifying, what was happening is, our number of nodes, if it is n, was directly proportional to the time complexity, right? But while downheapifying, our number of nodes got inversely proportional to our time complexity, and this led to a lower time complexity from n log n to log n, to O of n, O of n, right? I hope you understood this point. I hope you got the video, and I hope you understood why we needed the efficiency at all, right? So that is it for this video. That is it for efficient heap constructor. I will see you in the next video. Bye bye. Take care.